So that's the velocity gradient. Okay. So whenever we define strain, we defined it as the difference in squared line segments, right? Squared distances of line segments, right? And we went through all those manipulations, okay? And so, you know, if you remember, we showed that that's equal to basically, depending on our choice, in one frame it's equal to 2e, where that's E is the Lagrange green strain, right? dx, okay? And remember, we got to this by making in the substitutions into these equations, right? So we chose to express d little x in terms of the deformation gradient, worked through all those manipulations, and then defined, you know, ultimately we had something in the middle that was like d big X is equal to F transpose F minus I d big X. And then we said this is 2e. Remember? So that's all, we've done that already. Okay. So what I'm going to do here, I want to take the time derivative of both sides of this. Right? And specifically, since I got a lot of things that are equal to each other there on the right, I'm going to take the time derivative of this. Okay? Now, it should be clear that d big S is in the reference configuration. It's not a function of time, right? So derivative of that thing is going to be 0. Likewise, d big X is in the reference configuration. It's not a function of time. So that's going to go to 0. So really what I'm doing is I'm taking the time derivative of ds squared and the time derivative of d little x, d little x. So if I do that, remember, so then just using the chain rule and then sort of the same idea that, you know, this is d dx dt dx plus dx transpose d dx dt, right? Well, you know, this is the velocity, this is the velocity, right? So I really have dv dx plus dx dv, right? And then we had an equation for dv. dv was equal to L dx, right, the velocity gradient, transpose dx plus dx transpose L dv. And we've used this several times. The transpose of the product is the transpose of each of the components reversed, right? So that is dxt L dx plus t dxt L should be a little x right here. And then I can factor out the dx, the little dx's. And I have that L transpose plus L is equal to that guy. And this thing we're going to call 2D, all right, or D is equal to 1/2 L transpose plus L. And this thing is called the rate of deformation tensor. So it's the symmetric part of the velocity gradient, right? You know, you can symmetricize any tensor matrix by taking 1/2 its transpose plus itself, right? Yeah.
Can you come back to the previous page? Regarding that part, dBi,
Mm-hmm.
find L, dxj. What about the time part, the partial?
Yeah, so I shorthanded this thing. The real proper way to derive that guy is through the same way we did for the deformation gradient. In fact, if you have a copy of Malvern, or you get it, there's a picture in there, Malvern, page 146. So yeah, if you go and you look at that, it gives you this equation more from it gives you a picture that looks very similar to what we did for the deformation gradient, and you'll see that there's higher order terms up there that you're ignoring. It comes from a Taylor series expansion. But the way you can think of this is that, you know, it's not a derivative, it's just an incremental change in an instant of time, right? So you sort of, this is the velocity gradient that, you know, that an observer would measure in the deformed configuration without any knowledge of the trajectory of it's the instantaneous tangent velocity in the current configuration.
So it's kind of Lagrangian?
No, it's Eulerian. It's in the current configuration. So, yeah, maybe next time I won't be so lazy. I kind of figured that since you saw me do it the full way for the deformation gradient, that you'd sort of accept this, but it's the same. The right derivation would be to do what we did for the deformation gradient.